Welcome to the Chapter 9, Part 1 video, where we're going to be talking about combinatorics. This is following up from our introduction in class. So what we're going to learn about, multiplication principle of counting, permutations and combinations, and then I've decided to save subsets for in class. So the multiplication principle of counting, we already introduced this as the idea that we can have a certain number of decisions, and each decision has a certain number of outcomes that are possible. So S stands for our decisions and R stands for the number of outcomes. So if I had 3 decisions, then N would be 3. We have decision 1 or S sub 1, decision 2 or S sub 2, and then decision 3, which in our case, N would be 3. So it'd just be S sub 3. Okay, now the ... is because I don't know how many decisions there could be possible. And then notice the subscript of the S matches the subscript of the R. That's just identifying which decision we're making. So here, the little 1 means it's the first decision, and R is the number of options that we have for the first decision. So the subscripts are just keeping us in order. Okay, and then in order to find out how many total options we have for that series of decisions, we multiply our answers together. So in class, we talked about having 4 letters and choosing 3 of them and arranging them. And then we said, okay, so we have 4 options for the first letter, then we have 3 options for the second letter, 2 options for the third letter, and we multiplied 4 times 3 times 2. Okay, so the multiplication principle of counting is that when we have a certain number of options and a certain number of other options, then we multiply them together. So our example here, using the multiplication principle, if a license plate has 4 letters, digits, find the number of different license plates that could be formed if there's no restrictions on the letters or digits. Okay, so notice now we're using the American alphabet. We have 4 letters and we have 3 digits. So I'm making 4 and 3 means 7 decisions. Okay, so here's my license plate. I would start by making 4 letters, 1, 2, 3, 4 letters, and then followed by 3 numbers, 1, 2, 3, and all of those decisions will tell me how many license plates there could be. Okay, now when I'm looking at my letters, I'm choosing from the entire alphabet. So I'm choosing from A to Z. There are 26 letters in the alphabet. In my second one, I can use, again, any letter of the alphabet. So that's, again, 26 options. Now, if I couldn't use the letter that I used before, it would have gone down the way that the one we did in class did. But I can use, if I used A, I could use A again. So the next one, same idea, any letter A through Z. So I have 26 options. And then my last letter, again, I have the options A through Z, so 26 options. So for just the letters, I have 26, 26, 26, and 26. And then we go into the numbers. Now, we're tempted to say the numbers are 1 through 9, but 0 is a number as well. So we can choose any number from 0 to 9, and that is 10 options. How come we can't choose the number 10? Well, 10 is not a digit. So 10 would take up 2 place values for the license plates. It would be a 1 and a 0. So for one single digit of a license plate, we have the options from 0 to 9. And we can say that same thing for the other 2 places. Okay, now how do I know what to do with this? Because I have 26 options for the first letter, and then for every first letter, I have 26 options for the second letter. We know that we need to multiply this. So we're going to multiply all these numbers. That's 26 times itself 4 times, so 26 to the 4th times 10 cubed. I would put that into the calculator. 26 raised to the 4th power is 456,976 times 10 cubed. That is 456,976,000 different license plates that we could have. These are different plates. Okay, now the California state license plate actually has these same characters, but in a different order. We have 1 letter, 3 numbers, then 3 letters. So for California, if there were no restrictions on letters or numbers, we could have 456 million different license plates, okay? Now, there are some restrictions on license plates to reduce profanity and make sure that there is variety, but also acceptable words on license plates. And then we also have vanity plates where you can do a customization of any 7 characters. It doesn't have to be that same order of letters and numbers. So this is an accurate look at license plates, but not super accurate to how the DMV actually runs the license plates. Okay. Whoop, here we go. So if we can use the multiplication principle of counting, we talked about how we could also use factorials, and factorials are used with what's called a permutation. A permutation is essentially like shuffling. So we're looking at reordering or organizing a certain set of things, and we're looking at how many different ways I can shuffle something, okay? And when we shuffle something, we are essentially having n options for the first choice, and then n minus 1 options for the second choice, because shuffling means I'm not going to repeat, okay? And when we do that, we end up with n times n minus 1 times n minus 2, all the way down to 1, and we said that this is called a factorial. And so if we have something like 7 factorial, we start out 7 times, and then we decrease by 1 each time. 6 times 5 times 4 times 3 times 2 times 1, but not times 0. And really that times 1 is never going to change the answer, right? In order to do this on a calculator, you're going to go into the math menu, over to the probability menu. You have to click the arrow to get over there. And then option 4 is factorial. So if I wanted to type 7 factorial, I would type the 7 first, and then I would do this whole process to get factorial. Then you had equals, and 7 factorial equals 5,040. Okay, now in order to shuffle a full set, we would just use n factorial, but sometimes we're not shuffling the full set. Sometimes we're only shuffling part of a set, okay? So in this example, we're shuffling the full set. We want to look at rearranging the letters in the word computer to make a new word. And now by word, I'm not talking about a word in the English language. I'm talking about just a set of 8 letters in any order. Okay, so we're taking the letters from computer, and the first thing to do, it says 8, but I'm going to double count just to make sure. 1, 2, 3, 4, 5, 6, 7, 8. It is indeed 8 letters. And I'm also, when I'm counting, checking if there are any repeats. So C is not repeated, O is not repeated, M is not repeated, P is not repeated. And every time I come to a new letter, I only have to check the letters after that. So U is not repeated, T is not repeated, E is not repeated. And so I know none of the letters are repeated. Okay. Now, if the letters do repeat, the computation is a little bit different. We'll address that in class. However, in our case, I have 8 slots. I have 8 letters in the first spot. Now, one of those letters is used, so I have 7 options, 6, 5, 4, 3, 2, 1. So I can count this as 8 factorial. Into the calculator it goes, and 8 factorial is 40,320. And I'll call them words. But remember, these are not words that you would find in a dictionary. These are just an arrangement of 8 letters. Okay. So what would happen if I'm not shuffling the whole amount? Well, then we can use the permutation formula. And notice now in my permutation formula, we're dividing by the number that we're not shuffling. So n is the number that we're shuffling divided by the ones we're not shuffling. So if I had 8 letters and I only wanted to shuffle 4 of them, I say how many combinations or how many permutations in our case can we make with 4 letters out of this word? Then we would take n factorial divided by n minus r. Where does that come from? Well, I have 4 spots in our example. In the first spot, I have 8 options, 7 options, 6 options, 5 options. Okay, but I don't have any more options because for the rest, I don't really care what happens to them. So this I can do as 8 factorial divided by the ones that are missing, 4 factorial. So that's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, but then divide by the 4, 3, 2, 1. And so what we end up with is just 8 times 7 times 6 times 5. Okay. Now this formula is pre-programmed in your calculator in the permutation option, which is in the math menu, probabilities option 2. So in our case, I had 8 letters. I'm shuffling only 4 of them. I would do 8 permute 4. Okay, if we try that in the calculator, you type the 8 math over to probability. Option 2 is the permutation 4. You should get 1,680. And if you tried it by the multiplication, 8 times 7 times 6 times 5 should give you the same answer, 1,680. Okay, that's if you have 8 items and you're shuffling only 4 of them. Okay, now what makes this permutation a permutation is that it matters what order they're in. So having something that is well, let's use the word computer again. We'll just keep building off of that last example. If I have MPTC, that's different than MTCP, right? So the order matters. These are 2 different words. Earning first place is different than earning second place. Earning the title of president is different than earning the title of vice president, okay? So the place order matters for a permutation. If I switch 2 of these letters in my answer, it would give me a different answer. That's what makes it a permutation, okay? So if we look at the opposite, or the I guess equivalent, but the order doesn't matter, is called a combination. So if for a permutation, the order matters. For a combination, it doesn't matter. So in this case, it's just a selection. So I have a box of 8 markers and I want to choose 4 of them to use on my picture. It doesn't matter if it's the first marker I pull out of the box or the 4th marker I pull out of the box. Those 4 markers are going to be used in my picture. So the order doesn't matter. Or I can say I'm making a committee. Okay, then it doesn't matter if you're the first person in the committee or the last person in the committee, you're on the committee, you're all equal value, you're all equal leadership status, right? Not a first place, second place, president, vice president, where the changing that would actually change the leadership. Okay, so a combination, the order doesn't matter, all places are equal. And in that case, we have to divide by duplicates, because if I have something like CMTP, now TMCP is the same, okay? It's the same 4 letters. The order doesn't matter. So no matter how I arrange these letters, it's one option that I need to count. So I need to divide by the duplicates, and that's what this is here. So for every 4 letters that I arrange, I'm going to divide by the arrangements within those 4 letters. Now, you don't have to memorize this formula. It's already programmed in your calculator in the choose function. Okay, so to identify the difference between when do I use the choose function and when do I use the permute function, if the order matters, you're going to do the permutation. If the order does not matter, you're going to use choose or the combination. Okay, choose function is right next to the permutation function. So we're going to use the same idea. We have 8 letters, and now we need to choose 4 of them. I don't care what order they're in. I just want 4 letters. Okay. If I do 8, choose 4, I'm going to type in the 8, go into the math menu, over to the probability menu. Option 3 is choose. And if I hit enter, that should give me, don't forget to type your 4. That should give me 70. I don't think I said to type the 4. Okay, so notice there are significantly fewer options when I use the choose function, and that's because there are a lot of duplicates. Okay, any combination of the 4 letters, for a permutation, the order matters. So within there's going to be options for how to arrange the 4 letters. In a choose function, I don't care what order they're in, they're all in my hand, they're all available to me to use, and so they all count as just one option. Okay, let's look at an example here. An example of a choose function or a combination function is when we have 10 people and we have 20 people and we want to make a 10-person committee. Okay, so does the order matter? If you're in a 10-person committee, doesn't matter if your name was called first or third within that committee. No, it's equal membership. It's a committee, right? Everyone's on the same playing field. So in this case, order does not matter. No, that means we're going to be using a choose or a combination. Okay, we start out with how many people do we have to choose from? We have 20 people to choose from, and we are choosing how many of them? We are choosing 10. So we're going to do 20, choose 10, 20 into the math menu, over to probability, option 3, and we're choosing 10 of them, enter. We get an answer of 184,756. That is the number of 10-person committees. This is different. 10-person committees. Okay, now what would this question have sounded like as a permutation? Well, now those 10 places in the committee need to have titles. They need something that differentiates them from one another. So instead of a 10-person committee, if it was a president and a vice president and a secretary and a treasurer and so on, 10 different positions, if each position has its own title and each title is different, then we would have done 20 permute 10. Because now the order does matter. Whether I'm the president or vice president, I have a different role in this committee. Okay, so if the committee has titles, T-I-T-L-E, if each position has a different title, then I would do 20 P10. Now, if it's the same 10 people, I can make arrangements within that, right? So president's different than vice president. I'm expecting a much larger number. So I would do 20, math over to probability, option 2 for a permutation, and 10. Now the answer that comes out is 6.704425728 E11. Okay, we've seen this notation before. E11 means scientific, for times 10 to the 11th power. So that means in order to get an accurate answer, I would need to move this decimal place over 11 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so this is an order of magnitude with 0, 0, 3, 3, 3. So that's thousands, millions, billions. This is 670 billion options. That's insane, right? So from 20 people, in order to make a 10-person committee, I had 184,000 options. In order to make a 10-person officership where each person has a different title, there are 670 billion options. Okay, so permutations gives you way more specificity. Okay, so combination order does not matter. Permutation order does matter. When the order matters, I should have more options to choose from. Okay, that's it. I'm going to do the subsets in class. So I actually think that that should be where the notes end on Blackbaud. We'll do a couple of examples and we'll do a Math Excel at our next class meeting. If you have questions before then, please feel free to reach out to me.